Okay, we'll wait for a few minutes for others to join.
Hello.
Yes,
Hello, sir.
Santosh. Yes, I'm
Good
audible.
evening, sir.
Good evening. Am I audible?
Yeah, audible, sir. Today,
Oh,
what are the portions you are going to teach and cover, sir, in IC engine?
so you'll get to know. First of all, we will start with some. Just give me a few minutes. I'll brief. Okay.
Okay, sir. Okay, sir. Thank you.
Yeah. Okay. So welcome to the week 5 tutorial for the course IC engines and gas turbine. I hope everyone is able to hear me clearly. Can anyone of you confirm?
Yes, sir. You are audible.
Okay, thank you. So in the last tutorial, we finished with the energy transformation calculation, where we introduced the indicated power, brake power, mechanical efficiency, okay, uh, indicated thermal efficiency, brake thermal efficiency, and the mechanical efficiency, that is brake power to that of indicated power. So today we will start with specific fuel consumption, and we'll do some numericals. Then we will come across to the actual comparison between the actual and ideal PV diagrams. Okay, that how actually an engine works. And following, we will do some questions and some testing of an IC engines. Okay. So I hope everyone is regular to the video lectures by the professor on the NPTL as well as to the assignments. And those who have missed any of the tutorial sessions, I hope you are able to watch the recordings and see the PDF notes which are sent by the NPTL team in a Google Doc form, Docs sheet form. And if you are not able to see, you can also uh, check on my YouTube channel, that is NPTL with Varnit, in the playlist for the corresponding course, IC engine and gas turbine. You can see all the recordings, and in each video description, you can see the link for the Google Drive where the PDF notes are available. All right, so let us start. Let me share my screen. If at any point of time my audio goes off, not able to see my screen, please immediately point me out. Okay. All right. Okay. I hope my screen is visible now.
Your screen is visible, sir.
Okay. Okay. All right. So we discussed about what is brake power, what is indicated power, what is mechanical efficiency. Okay. And mechanical efficiency in terms of mean effective pressures as well, for brake mean effective pressure and indicated mean effective pressure. Now let's come to specific fuel consumption. Specific. I think my video is not visible. Just hold on. Now might be. Yes, great. Specific fuel consumption. So what do we mean by specific fuel consumption? That for the given input power, how much amount of fuel is required. Okay. So if I say both, the power can be in form of two forms, either indicated power or brake power. Okay. So if I say in terms of indicated, specific fuel consumption can be ISFC. So I'll write the short form, that is SFC. ISFC is the indicated specific fuel consumption, that is mass flow rate of the fuel to that of indicated power. Okay. And what is brake specific fuel consumption? It is mass flow rate of the fuel to that of brake power. Okay, to that of brake power. Okay, and the unit is, if I say my units are kg per kilowatt hour, kilowatt hour. Okay, kg per kilowatt hour. So if I say, if in my actual amount of power which I am getting is nothing but a from the brake power, whatever I am getting on the wheels, okay, or wheel drum of the vehicle, actual in reality. So the brake specific fuel consumption, if more amount of brake power is there being generated, then less amount of brake specific fuel consumption is required. That means, and in the less amount of fuel, I'm able to achieve more amount of brake power. If I say, if my brake power is high, eventually this denominator is high, my brake specific fuel consumption is less. And if I say my fuel consumption is also less, then also my brake specific fuel consumption is less. Okay. So what can I say? It gives the, what it actually tells is basically that it gives the performance of an engine, performance of an engine. And from here only we came across with the term of economy. Okay. What is the economy or mileage of a vehicle? Okay. So it gives, let me write, it gives performance of an engine. Okay. So whenever you go and purchase a vehicle, if you see over the catalog, you see various specifications are written on the catalog for that vehicle. So there is a specific fuel consumption also written. If you next time see, the lesser the specific fuel consumption will be, the better the engine will be. Okay. You don't want lot of fuel to produce the same amount of power in, because fuel is an economic source and it is limited in nature. You want in lesser amount of fuel, how much amount of economy or average or mileage you can produce from that vehicle. Okay, that's why we directly as a consumer we ask that what is the mileage or what is the economy of that vehicle. But in actuality we should ask what is the brake specific fuel consumption of that vehicle, being an engineer. Okay, why I am saying, if I say, let me write first the point note, if my brake power is high, that implies my brake specific fuel consumption BSFC will be low. That means my economy of that vehicle will be, economy of that vehicle on me of that vehicle will be high. Okay. Now why I'm saying this, if let us take one example here. Example, if I have a car one, okay, whose BSFC is equal to 0.3 kg per kilowatt hour. Okay. And car 2, whose BSFC is 0.03 kg per kilowatt hour. An interesting thing is that both gives an average of 20 kilometers per liter. Both gives an average of 20 kilometers per liter. Now you tell me, by looking this, if an examiner asks a question, which engine is much better? Can anyone of you tell me which engine is much better, of car 1 or car 2, and why? Just now explain from the concept. So Santosh, what do you think? Which engine will be better? Tennyson, Swararama,
Zero, second gas,
second engine. Okay, why?
uh, because it takes a very small amount of fuel for the same power.
But both the engines are producing, are giving the output of the mileage as 20 kilometers per liter. Now, why still you are saying that second engine will be better?
Okay. Um,
Are you getting my point? What I'm trying to ask?
okay. Let me think.
Yeah. So there is a catch here. I am saying the economy will be better, but mileage is same. My second car is having a lesser brake specific fuel consumption. That means my economy of the engine is better. My engine is much better. Although the mileage produced by both the engines is same. So let us say the car one is a smaller car, like let us say it's a hatchback car or it's an Alto of Maruti Suzuki. Let us say take for an example. Whereas car two is a BMW car. Okay, any of the series you can say, a high-end car or even the mid-range. The car two is much better. All the both are producing the same average. The reason behind this is in a car you have lot of components which are running in the engine itself. Okay, so engine of a high car 2 will be a much bigger engine, okay, compared to an engine of a smaller car, that is car 1 here. Okay, so to run such big amount of engine, you just need 0.03 kg per kilowatt hour of brake specific fuel consumption. Through the running of that engine, you are able to run recharge your battery of that system, as well as you are able to run the electronic components of the system, multiple electronic components. So if I say in reality, in such small amount of fuel, I am able to run hundred of components of that vehicle. Whereas in carbon, with a bit 10 times higher amount of fuel, I am able to run only 10 components of that vehicle. Although the engine is producing the same output as a mileage. But the running of the component inside the vehicle for car 2 is 10 times or 100 times higher compared to the car 1. That's why if you see a high-end cars have a very low specific brake specific fuel consumption compared to a low-end cars. Okay, though they are producing the same mileage as an output. So whenever you go next time to purchase a vehicle, don't see what is the mileage of the system. Being an engineer, don't ask what is the mileage of a vehicle. Ask what is the brake specific fuel consumption of a vehicle. Then you will get to know that which vehicle is much better to run in lower amount of fuel than multiple amounts of components of that vehicle. Okay, I hope this is clear. Any doubts in understanding this? So I'll write here the point. Car 2 is much better since or because for less amount of fuel, multiple components of the car are able to run for same mileage. Okay, all right. Next part, how do we get the average piston speed? average. So that was part, I think part 5 or 4, part 4. In last lecture we did till part 3. This is part 5. So that is average piston speed. Average. So average, what will be the piston speed? That with what speed the piston is able to displace in particular amount of time. Okay. So we say Vp is our piston speed, that is in meters per second as per SI unit. That will be 2 times of the length. I am talking about speed, not velocity. So speed is a scalar quantity. And total distance in into n by 60. That is in how many revolutions in 1 seconds. So 2L is the total distance covered into n by 60. That means this is your revolutions in 1 second. Yes. Any doubt? Someone unmuted. Santosh.
Sir, hello.
Yes.
Hello. Sir, what is mean VP stands for piston volume?
VP is this average piston speed. Okay.
Piston speed.
Yes. Okay. I've written the symbol here.
Okay. What is mean by 2L length? L mean
2L is
L stands for length.
L stands for the length covered by the piston in a cylinder mechanism. So the from top dead center to bottom dead center. Okay.
Okay.
Okay. All right. So this is your L. Okay. Now what will be relative efficiency? Part 5. I am telling all these because I'm going to give a numerical now. No, sorry, part 6. Part 6. Relative efficiency. The symbol is eta relative. So eta relative is nothing but brake thermal efficiency to that of air standard efficiency. Okay. So when I'm saying what is brake thermal efficiency, we studied in last tutorial, brake power to that of heat radiated per second. And what is air standard efficiency? If you go for any of the cycles, suppose I take a dual cycle, what is the air standard efficiency of dual cycle? 1 by 1 by 1 minus 1 by r to the power of gamma minus 1 into alpha rho to the power of gamma minus 1 to that of alpha minus 1 plus gamma into rho minus 1. Okay. All right. So this is your relative efficiency. You can use auto cycle efficiency or any of this you can use. Suppose I'm taking dual, or if you want to say auto or diesel. Okay. All right. Now I'll give you a numerical for on based on this. Fuel consumption rate of petrol engine is 3 kg per hour with calorific value of fuel 44.1 megajoule per kg. Power developed by engine is 11 kilowatt. Brake thermal efficiency BTH of engine is 50% of its air standard efficiency. clearance volume of engine is 9 to 25 centimeter cube with engine ratio of 1.5. You need to determine cylinder dimensions. Determine cylinder dimensions. All right. Take few minutes and tell me the answer for this. I'm in the class itself. You can ask me if you have any doubts. Everything I have explained, whatever the terminologies are. This is 44.1. Okay. Done? Anyone has done? I hope everyone is able to access the PDF and the lecture recordings tutorial. Can anyone of you confirm if someone has watched and seen the PDF? Santosh, were you able to access the recordings and the PDF notes?
Yeah, sir.
Can
I
you-
am.
Okay.
I am
Okay.
able to see your recording and view.
Okay. Thank you.
Okay, thank you.
Okay, anyone came up with the answer? Anything? Did you got the answer? $61.69. What is this? L or D? Swara, what is this? D. Okay. I think this should be L. 61.9 centimeter, not mm. Because you are given the volume in terms of centimeter cube. All right. Let us do. Okay. Solution. Let us see. So it is given that you are having fuel consumption rate 3 kg per hour. Calorific value is given, so you can get the heat added per second from this. Power developed by the engine is 11 kilowatt. Basically, the brake power is given. Brake thermal efficiency to that of air standard, that is relative efficiency is given 50%. Clearance volume is given, and L by D is given as 1.5. So everything is almost given to you. So let us see. So heat added per second will be what? As I said, mass flow rate into calorific value. So what is mass flow rate? It is given to be 3 kg per hour. So if I want to convert per second, okay, 3 by 3600. And what is calorific value? 44.1 megajoule. So in kilojoule, if I want to do 44100, so I get 36.75 kilowatt of heat added per second from here. Okay. What is brake thermal efficiency? It is brake power to that of heat added per second. So we know that what is the brake power given? 11 kilowatt. 11 to that of 36.75. So we get as 29.93 in terms of percentage brake thermal efficiency. Also, what is BSFC, brake specific fuel consumption? If I want to calculate, that will be mass flow rate to that of brake power. Mass flow rate to that of brake power. If the examiner asks that, so it will be mass flow rate is given as 3 kg per hour. So let us keep it in kg per hour only, and brake power is how much? 11. So this gives you 0.273 kg per kilowatt hour. Kg per kilowatt hour. Okay. A brake thermal efficiency you have got. This is an extra thing I have calculated. Brake thermal efficiency you have got 29.93%. And relative efficiency, or it is given that brake thermal efficiency is 0.5 times of air standard. Okay. And what kind of engine it is? It is a petrol engine, basically an auto cycle. That means auto cycle is given to you. So you know what is air standard efficiency of an auto cycle? 1 minus 1 by r to the power of gamma minus 1. Okay. What is brake thermal efficiency? You have calculated 0.2993, 29.93%. And gamma, you know that is 1.4. From gamma is 1.4. So from here, R will come out to be 9.79. And you know that R is equal to 1 plus 1 by C. So from here, your C will come out to be 8.79. And C is nothing but VC by V swept. Okay. So C is VC by V swept. C is 1 by 8.7. Sorry. All right. So whatever in the fraction I put 1 by 8.79. So V swept is given to you how much? The sorry, clearance volume is given as 9225. So VC you know now. So 9225 by Vs is equal to 1 by 8.79. So from here you will get the swept volume, and swept volume is nothing but pi by 4 d square L. Okay, pi by 4 d square L. And since L by d is given as 1.5 in this, so L will be 1.5 times of d. Put this L here. This will be pi by 4 d square into 1.5 d, and V swept is, from here V swept will come out to be, V swept is 9225 into 8.79. Put this value here. So from here you will solve and get your D is equal to 40.98 centimeter and L is equal to 61.9 centimeter. Okay. Answer. All right. Pretty simple question. Any doubts in this question? Everything was very much self-explanatory. Everything was given in the question. You just have to put the values and get the answer for the question. Any doubts? Please ask so that we can start to the next topic. Any doubts? All right, no doubts. Then let us come. So far we were dealing with the scenario of Otto cycle, diesel cycle, dual cycle, and all those scenarios were idealistic scenarios. Okay, they were not the real scenario how an engine works. Okay, so far it was an idealistic scenario where we were making the pressure volume plots in an ideal scenarios. But in actual scenarios, the engine works a bit differently. Now let us understand the difference between the theoretical and actual engines. And I'll start with the comparison between the Otto cycle, the very basic cycle. Let's come to the topic of actual and ideal PV diagram. Actual and ideal PV diagram. So let us say the first is theoretical or ideal. Theoretical, which we have been studying. How does that look like? We have been studying it multiple times. We have made this plot of pressure volume for this pressure and volume. We say that our first process is isentropic compression. Okay. Then we say that heat addition at constant volume. Then we say that, sorry, expansion or power stroke. Okay. Isentropic expansion. And last is heat rejection at constant volume. But there are two other processes also, suction and exhaust, which we don't make here. Why? Because if you see, suction starts in the engine, the volume starts increasing. Let me just, so the volume start increasing initially at the constant pressure. No, not here. At the constant pressure. Okay. As well as the exhaust also happen at a constant pressure when the exhaust stroke happens when the pressure is constant. Okay, coming to the initial part only. And if you observe, they don't give any work. Okay, though both have same amount of area. If you see, so net work for, if you see, for this is also this, and for orange is also this. So one is positive work, one is negative work. So both the works cancels out. Okay, the net work is, there is no network. It cancels out. That's why we don't generally make this suction and exhaust process in the PV diagram cycle. Okay, so although in the representation we will depict, this is your suction stroke and this is your exhaust stroke. This was your isentropic compression, heat addition and heat rejection. Okay, heat addition and heat rejection at constant volume. Okay, this was PV raised to the power of gamma. Let me use some another color. PV to the power of gamma is equal to constant. One is isentropic expansion and one is isentropic compression. Okay, these were the process. Let me write the point for this too. Both are same and don't cover any area that is work net is 0 for both the processes. Therefore, we don't show the process in the plot. Show these processes in the graph. So this was an theoretical which we have been dealing with so far. Now let us understand the actual cycle. Actual cycle. This is very important. Please understand the process by process. I'll be explaining process by process what is happening during suction, compression, heat addition, expansion and heat rejection, and again exhaust process. Each process I'll be explaining in very detail. Please listen it very carefully. If you find doubt at any point of time, you can ask me, stop me and ask me. Okay, but please understand. Okay, so let us understand. So this is your pressure volume plot. Okay, so first process, suction process. Suction. Okay, so let me first draw the idle cycle in a dotted format, from which we will take a reference and draw our actual cycle. Am I drawing wrong? Okay, let me draw once again. All right, and this was okay. Now, if you observe, suction only happens when I explained in the first tutorial that how the engine works. Suction will only happen in the cylinder if pressure inside the cylinder is less than the atmospheric pressure from which the air-filled mixture is entering. Okay, if the pressure is less than the atmospheric, because the air-filled mixture is getting entered into the cylinder at a atmospheric pressure, and if the pressure inside the cylinder is lesser than the outside pressure, then only because of the pressure difference the suction will happen. and its variation depends over the piston speed. Higher the piston speed, less the pressure, as per the Bernoulli's law. Okay, so pressure is inversely proportional to the velocity or speed. Okay, so when the pressure inside the cylinder, if we say this is our atmospheric pressure, this is our PATM at which the suction has started. If the pressure inside the cylinder is less than the atmospheric pressure. So how the actual suction will happen is basically the suction will happen like this. Okay, so pressure is less, and finally when the whole air fuel mixture has been filled, then the pressure will achieve and there will be no intake of the air fuel mixture inside it. Okay, initially pressure was less and in the outer air fuel mixture was at higher, so therefore actual the air fuel mixture tried to enter till the volume expanded, and then because of the the pressure built because of the air fuel mixture which has entered is now achieving its atmospheric stage, the whole suction process will stop. Okay, so this was your actual suction process. So let me actual suction, actual suction. Let me write here as well about the suction. In actual suction, actual suction will take place only if pressure inside cylinder is less than P atmosphere. Okay, and its variation is depends upon speed of piston. Okay, all right. So what can we say that initially the piston speed was less, it was trying to achieve from top dead center to bottom dead center. We have seen this the time in the time analysis in the previous tutorial that piston speed is 0 at the dead centers. Initially try to achieve the speed till the mid or some length we achieve a maximum speed towards the mid side. Then finally, so it was initially it was accelerating and then finally it was deaccelerating. Okay, so what can we say? This is a section till mid where acceleration was there, accelerating, and then finally from here till here it was deaccelerating. Okay, deaccelerating. All right, the piston is deaccelerating. Okay, and pressure inside cylinder is less than atmosphere. So I can also mention that point. Pressure of cylinder is less than the atmosphere. Okay, in the actual suction process. All right. So here at these points, I should use which color? This one. So this is a point where V is 0. This is a point where V is 0, and this is a point where V is maximum. Okay, V is maximum. All right, and pressure is minimum. So that is why the pressure is minimum here. Pressure is minimum as per the Bernoulli's law. So that is why the pressure in the whole cycle is minimum at this point only. P minimum. Okay, P minimum. I hope this suction process is clear. Yes or no, please, so that we can process to the compression one. Is it clear or not clear?
Yes, sir. It's clear.
It's clear. Okay, all right. Now let's come to the compression process. So what happens in the compression process? The process in actual scenarios, it cannot be adiabatic. Adiabatic is something very fast process, okay, without any heat exchange. But in actual, if you see a real vehicle, there are water jackets around the cylinder. Because if temperature is so much high, the material of the engine will melt down. Okay, so simultaneously, the water jackets are there or liquid jackets are there, which takes out the heat out of the system from the engine parallelly. Okay, so that temperature should not be that much high. And due to this heat transfer, you want to give more input work required for the compression process, because compression is a work absorbing process, not work producing process. Okay, so during the compression, the work required is higher compared to the isentropic or ideal scenarios. Okay, for the compression process to happen. So if you see the heat, and it is not an adiabatic process, it's a polytropic process where PV raised to the power of n, and n is your polytropic index there. Okay, n is your polytropic index. So the process will look like, if you say from here to here, originally from original dotted line, this line is a bit above, it's bit above. So let us see, let me write here first. Use the compression process. Compression. If I make a small diagram once again here for PV for showing this process. So ideal scenario was this, and actual scenario is this. So when ideal scenario was there, so the actual work done for this process from this area under the graph was this much. When real scenario came, the area under the graph was this much for the same swept volume. Why I am not using till here for the same swept volume. So there is an increment in the work, and that increment is nothing but this small increment. So there is an extra amount of work which is required for compression to happen. Okay, because if you see, dq is nothing but du plus dw. In adiabatic scenario, heat transfer is zero. So whole of the internal change in the temperature or internal energy is nothing but or equal to the net work absorbed by the compressor. Okay, to increase the temperature. But now you are not maintaining heat interaction to be zero because water jackets are also there surrounding. So this cannot be zero. dq cannot be zero. So there will be some amount of extra amount of heat which has been taken out. dq is not able to maintain zero. So extra amount to maintain dq equal to zero. If you want to make dq equal to zero, you need to give this value to be higher so that it balances out. You need to give, in practical sense, you need to give more amount of work to the engine so that your dq is equal to zero. Okay, so in mathematical and practical form, this is the way to understand. Okay, let me remove and make a clear. Oh, I think this is the maximum limit. I'll use the another. Okay, and this is the extra amount of work done. More work is provided. And if in sense of the polytropic index, if you have heard in the thermodynamics, you know that polytropic index is greater than adiabatic index and it's greater than the isothermal index, that is 1. N is greater than gamma is greater than 1. In thermodynamics, we have studied this. Those who are confused, you can check out my tutorial for thermo as well on the channel. Okay, since N is greater than gamma, because this process was PV raised to the power of N, polytropic process equal to constant, and this process was PV raised to the power of gamma is equal to constant. And in actual scenario, it is not an idle. So this was the number one. This was number 2, let us say this is 2A. Let me use this color, 2A. So this was 1, this 2, so this is 2A. Okay, 2A. Let me make this, okay, 2A. All right. And I'll write this point here as well. In actual compression, is not adiabatic because heat is continuously taken by cooling water or the jackets, and due to this heat transfer, more input work is required for compression. This implies more area under PV diagram. Okay, more area under the PV diagram. All right. Also, we can write in that sense dq is equal to du plus dw, so that this is not equal to 0. You need to increase the work. Okay, you need to increase the work. All right. I hope this is clear. Compression process is also clear. Any doubts? Actual suction, actual compression, both should be clear very well. If there is any doubt to anyone, please ask at this point only. Okay,
Sir, it's clear.
it's clear.
Clear.
Oh.
Okay.
Okay, so let us come to the process of heat addition. Just give me a minute. You try to understand and give me a minute, please. I'll be back. All right, let's be back. Now let's come to the heat addition process at constant volume. Third, heat addition at constant volume. So what is happening when we say that our piston is at the top dead center after the compression? We say that the piston at that instant we start the spark ignition. But in actuality, it is not possible to maintain that piston to be at that instant and fuel the as soon as the fuel has been compressed, the spark to be ignited, because no one can sit inside in the actual scenarios and see that at same point there will be some microseconds gap when the piston will be reaching to the top dead center and will moving back to the bottom dead center during the expansion process. Okay? So there will always be a microsecond gap between that. So what happens? The spark doesn't begin directly when the piston has reached at the top dead center. Spark begin just before the top dead center position. Okay, so that and the change in the volume is in such a way that there is a minimum volume change when the piston has moved from top dead from bottom to top when it is coming near to the top and then coming back to the bottom. Okay, there will be a very minimum volume change. It won't be constant volume, but very minimal volume change will happen. So in actual scenario, what happen if I say this is my PV plot and if I want to show this process, so what happens when the piston is reaching near, so actual scenarios was this and this was the constant volume, but just before the heat in, spark will be provided and for a minimum volume change. So the volume was here and here, so volume change is very minimal. The heat addition will happen. Okay, heat addition will happen for a very minimum volume change. Okay, and the pressure change will also be there. Okay, pressure has increased in the cylinder. So I'll make once again this diagram in a clear way. Let me write the point first. What I'm trying to say, in actual heat addition, will begin before end of compression. Before end of compression and try to make it in minimum volume change as sparking is very fast phenomena. The sparking is very fast phenomena. So here combustion is neither constant volume nor constant pressure, and this occurs at a very minimum displacement of the piston. Okay, so what we can say here is that, let me first make the diagram. What I'm trying to say, okay, so this was 2, this will be 3, 2a, I think, yeah, 2a and 3, this will be a 3a. So this is a pressure increment and this is a very minimum. I should not use blue color. This will be very minimum amount of volume change happened. Okay, all right, and this is your direction of your cycle. Okay, So what I'm trying to say here is that basically if I have a cylinder, if I make a cylinder, two scenarios of a cylinder, this is top dead center, this is my spark plug. Okay, piston is almost, when the fuel is being compressing, okay, from bottom dead center to top dead center it is reaching. Okay, so this point position is A position to A position. Okay, and whole of the fuel is being compressed, so that means it is, the temperature is quite high. So sparking is happening at 10 degrees Celsius before, 10 degrees before the top dead center of the 10 degrees of the crank rotation. Okay, so sparking happens, sparking begins at 10 degree before top dead center. B is before top dead center. Okay, so what is there? If you see the cylinder from the top, if you try to see the cylinder from the top, what is happening in this cylinder? The spark is, plug is here. Okay, and whole of the fuel is currently at a very high temperature state and just ready to ignite, and you just immediately provided the spark. And then in the other scenario, pressure has increased. Okay, and this is your, and it's going back. Okay, in this side. Okay, from the top dead center, TDC, the spark has already been begun, and the flames of the fuel has started to burn, and flames has been trying to form. Flames are trying to form. Okay, flames are trying to form. So if you see from the top, this was your spark, and the flames are inside the cylinder at this scenario. Okay, this is, let us say, some CA position. Okay, CA for a very minimum volume change. If you see from this position to this position, the volume change is very minimum. The volume change is very minimum. Okay. Okay. So let me, so this is a process where heat addition, time for the heat addition has happened. Okay, and ignition ends at after 10. Let me write here, ignition ends at 10 degree after TDC. So when it is coming back, 10 degree after TDC. First it was going above and then it's coming back. So let me make this in this graph, or main graph. So from here to the position this. Right. Let me first hope this line once again. This is not a straight line, some curve is there. So this was a point 2A and this is point 3A because this point was 3. Okay, 2A and 3. And here actual heat addition is happening. Heat addition. Okay, I'm not writing this time at constant volume. This is not happening at constant volume between 2 to 3. Okay, I hope this process is also clear. Suction, compression, heat addition. All these three processes are clear now. Let me make the direction of the cycle. This is the direction. Okay. All right. Now we will come to the expand. Let us see one. If I want to give you an example, let us say a short example here. I'm saying theta is 10 degree. I'm saying now that at 10 degree before and 10 degree after the top dead cycle, the spark begins and spark ignition ends. Okay, my engine revolution is 2400 rpm at that position. 2400 rpm. What will be this time for the heat addition, which I'm saying? This time for the heat addition. Can anyone tell me? We have calculated this kind of scenarios, this time analysis we have done. So you have to use the same concept. So time is theta by omega in terms of polar form. So time will be theta by omega. Theta is 10 degrees, and in terms of radians, it will be pi by 180 and 2 pi n by 60, where 2n is 2400 by 60. So it will come out to be 1 by 1440 seconds. So you can see that how in a very fraction of seconds, in a millisecond, this scenario is happening. Sparking happened and the ignition of the fuel started. Okay. The next process is actual expansion process. Fourth process D, actual, sorry, expansion. Let us say just the expansion is same like compression. So for compression is a process which is work absorbing. Work is being absorbed. Whereas expansion is a process where work has been produced. The power stroke produces the work basically. So as during the compression, the water jackets were there which were rejecting out the heat from the system. So for that, we need to give extra amount of work to the system, to the cycle. Similarly, that heat that has been rejecting is also because water is taking that heat from the compression process, but water jackets are still around the cylinder itself, around the engine cylinders as well. So from where the heat has been extracted out from during the compression cycle, same amount when the expansion stroke is happening, the temperature is dropping from higher to lower. So that high temperature water will provide the heat back during the expansion process. So what will happen? The amount required during the work produced was lesser than the work produced from the ideal scenario. What I want to say is that if you see a PV diagram, let me make PV. So this was your, suppose, process 3 to 4 in the ideal scenario. So area under the graph will be somewhat this. So I think I made some extra. Let us make till here only. Area under the graph is somewhat here for this process, this much. Okay. But in actual scenario, the work produced will be a bit lesser. Okay. Work produced will be a bit lesser. So this was a scenario of PV raised to the power of gamma is equal to constant. That is an isentropic expansion. But this is a process of polytropic. PV raised per n is equal to constant. And this is the loss of work. Loss of work. Okay. And we know that polytropic index is greater than gamma. So we have seen the PV plots in thermodynamics that the slope of PV plot during the expansion is producing lesser or higher slope. Higher slope. Okay. It goes. So there is a clockwise cycle of happening if you have seen the processes. I don't know. in your thermo, but I'm explaining in terms of physics as well. So whatever heat, let us say from an example, we provided 100 kilojoule of heat. 10 kilojoule came from the, because we have added the heat in the 2 to 3 process here. Okay, heat has been added here, heat addition. Okay, we provided 100 kilojoule of heat from actual heat scenario, but 10 kilojoule of heat was also comes from the water jacket, which was during process from 1 to 2. You wanted to provide only 100 kilojoule, but 10 kilojoule extra was there. So that means 110 kilojoule of heat was there. Okay. So in the ideal scenario, the water produces a bit higher, which is an isentropic scenario, but in actual scenario, it is less. So if we say in this sense, dq is equal to du plus dw. So you wanted to have 100 kilojoule of heat, but you had, oh sorry, you wanted to have zero change of heat, isentropic expansion, adiabatic reversible, but you didn't had an uh, dq to be zero because it was positive 10 this time. Okay, you had an extra 10 kilojoule of heat from the water jacket. Okay, so to make it lesser towards the zero, it was positive 10, you want it to be zero, you need to decrease the work mathematically also. In mathematical sense, you understand that if you want from positive to zero, you also need to decrease the work produced. So this is a real sense that water jacket is also providing some extra heat, which is not required, and unwanted heat. And because of that, the work produced will be a bit lesser by the actual cycle. Okay. Then from polytropic index also we understood that polytropic index is greater than the adiabatic index. Okay, so this was 4 and this will be 4a. Okay, 4a. Okay. Is there any in actual expansion? In actual expansion, work produced. So same lining we will use. It's not an adiabatic process. It's not an adiabatic process. In actual expansion is not an adiabatic process. As water jacket has provided extra heat into the system, so same language, and due to this heat transfer and due to this network produced, not network, work produced from this process, work produced is less. Okay, so when I say dq is equal to du plus dw for the process, there I said that dq is non-zero, and let us say dq is non-zero and heat extraction was minus 10 kilojoule, let us say minus 10 kilojoule. So you wanted to come to zero or non-zero value. Initially it was non-zero and you want to come it to a zero, non-zero, and you want it to come to a zero, you need to increase the work. You need to increase the work. But here the heat added has been extra. So here again heat is plus 10 kilojoule extra, non-zero, and you want it to come back to 0 kilojoule. You want to come back to a 0 kilojoule. So for this, you want to decrease the work. Okay, in mathematical sense also. Okay. All right. Not isentropic. Huh? And is not adiabatic. Let me write not adiabatic. Isentropic is a much better. Isentropic. All right. So this and let us make this in an actual cycle also. So work produced will be a bit lesser. Okay. So this point is 4 above, and this will be 4a. Okay, 4a. All right. Not till here. I think I should not have made till here because exhaust process also will be there. So let us make it till. Okay, this was 4. This will be 4a. 4a. Okay, actual expansion. So this will be the direction of the cycle. So this is PV to the power of n is equal to constant. Actual. Okay, actual scenario. Now again come back to the heat rejection at constant volume. Same scenario, heat rejection. Heat rejection will also be same. So it will not be happening at a constant volume. There will be a slight volume change will be there because the piston speed is very fast. So we can directly make here same process with a minimum volume change. Okay, 4a, and finally is the process. So this is an heat rejection at actual scenario. Heat rejection. Okay, and finally, as the suction happened, exhaust will also happen, and exhaust will only happen when the pressure inside the cylinder. I told in the tutorial first that exhaust happen when the pressure inside the cylinder is slightly higher compared to the atmospheric pressure, and because of the pressure difference only, the exhaust gases will move out from inside. Rest 10% of the gases will move out from the cylinder to the atmosphere. So eventually, the pressure will be a bit higher and finally come to a atmospheric scenarios. And this is your exhaust process. So let me use some another color. Actual exhaust. Pressure inside cylinder is greater than P atmosphere. Okay. Okay. I think this is pretty much clear now. Any doubts in understanding the processes? Very important cycle for understanding that how the actual PV auto cycle works compared to the ideal scenarios. Okay, compared to the ideal scenarios. So let me write the summary points once again. Summarize. So the first point is actual PV diagram is consisting of two areas. Two areas. One is positive area. If you see this one whole, this one is a positive area because it's a clockwise formation from this to this. Okay, clockwise formation is happening. And other is a negative area. That is an anti-clockwise formation is happening. A negative area. Okay. So this is a negative area. Let me write these also, positive and negative in this graph. Let us use some another color. This is positive and this is negative. Okay. So the above area is positive and below one is a negative area. Negative area. Two areas. One is positive and other is negative. And this negative area is also called as a pumping loss because you have to provide some extra input during suction and some extra amount of work been there during the, which is a negative work which has been there because volume is being decreased. So it is also called as a pumping loss. Pumping. So negative area is also called as a pumping loss. Pumping loss. Okay. Hence, in actual scenarios, the indicated work done will be, because indicated work done comes from, we have understood in previous tutorial that indicated work done comes from a PV diagram, and brake power comes from an whatever the power you have generated over the wheels or the brake drums. Okay, this is a pumping loss. Hence, we can say that actual indicated work done is your input power, indicated power, that is indicated work done per second, is nothing but net area in actual PV diagram is nothing but your positive area or gross work, also we can say gross work, positive area or gross work minus the pumping loss. Pumping loss. Okay, so we can also say this pumping loss to be a negative work. Okay, and positive area is your gross work. All right, so pumping loss is nothing but the total amount of energy required to overcome the resistance from the actual suction and actual exhaust stroke. Pumping losses, let me write that point, the total amount of energy required to overcome the resistance for the actual suction and actual exhaust stroke. Okay, actual exhaust stroke. All right, so this is nothing but your Otto cycle PV area. Okay, in solving for the numerical, and this is the extra pumping loss which you have, which is need to be extracted out. Okay, so this was your indicated power in actual. Okay, actual indicated power actual, and what was indicated power theoretical? Theoretical was nothing but your only positive area of the PV diagram. Okay, positive area of the PV diagram. Why an actual scenario come? Because there are presence of water jackets which provide heat interactions, and these water jackets are nothing but connected through your, if the water is taking some heat, the heat has to be taken out of the water itself. And if you see the radiator which is in the front of the vehicle of a car, if you see there is a radiator in front of the car, as the car moves at a higher speed, due to the air passing through that radiator, the fins mechanisms are there over the radiator, that heat, the water passes, or the liquid, whatever the fluid is there inside that, that is passing through that, is taking out the heat from that jacket. Okay, liquid jacket. So if I say in this scenario, first let me make one thing. PV diagram for a theoretical sense was nothing but this one. Okay, theoretical, but PV diagram for actual one was nothing but okay, was something like this. So let me make it a bit clear. This is your positive work, this is your negative work. Okay, negative work. Okay, and one thing I have to add here is that how this water mechanism happens in the jackets. So there are okay, there are water jackets here. Okay, liquid jackets are here for cooling the engines. Jacket for cooling ice engines. Okay, there is a piston somewhere if you see here. Okay, and thus these water jackets are connected through a radiator. Okay, in front of the car. So it's a mesh and fin base like a, if you see today in your vehicle, you will see this kind of scenario. Okay, from which it passes through pipes and get radiator. Let us say it is a radiator. And this is nothing but your heat exchanger, which you will understand in your heat transfer subject. Okay. And this heat interaction, if someone asks what will be from the water jacket, it will be mass flow rate into Cp of that coolant into change in the temperature. Okay. Change in the temperature. Next one point I want to add here is that there is a term here that is called as a diagram factor, which is asked sometimes. Diagram factor. Because there are two diagrams, actual diagram and theoretical diagram. So it is nothing but equal to indicated work done of an actual diagram to that of indicated work done for theoretical diagram. So I have written the indicated work done of actual and theoretical here. Okay, these two. Let me highlight them. Okay, these are the indicated work done of theoretical and actual. Okay. Next, one more point I need to add. Actual PV diagram. And now someone can ask me that how you make this if I want to make in a practical, this is for explanation, but with values I want. What will be the pressure? What will be the volume? How you can measure the pressure in the sense there is a device that is called as a Bourdon tube, which is connected to a piston in the external to the cylinder. Okay. That is nothing but your spring system. Okay. So let me write one thing. Bourdon tube, about the Bourdon tube. Actual PV diagram. Is plotted by an experiment in which a pressure spring that is also called as a Bourdon tube, where spring has a stiffness of SP, that is pressure spring stiffness. Okay, is used, which is attached to piston. to piston, which is attached to piston. In actually, let me write. So suppose this is your piston cylinder horizontally. Okay, this is your top dead center. The piston is supposed somewhere here. Okay, and there is a tube kind of mechanism here with some spring, which is a spiral kind of scenario, or not like this. Okay, and as the piston moves, the pressure changes, and this pressure spring mechanism flaps in or flaps out. Okay, so there is a hole here. Okay, this is a pressure spring. Okay, so stiffness is SP. Okay, there is a pencil attached here, which is connected to it's in the front of a white sheet or something, which will help you to make the plot. Okay, the PV diagram. So this is your pencil or marker, whatever you want to say, which is there, and the compression suction happens between these two. Okay, so to and fro. Okay, movement happens for compression and suction. Sorry, compression and power stroke, exhaust, not exhaust, expansion. All right. So is it clear till here? I have to add one more point. Another point is that, any doubts? Guru Prasad Rao, you unmuted.
Sir, could you please discuss the numerical examples given in the uh, assignment problems, sir?
We can discuss towards the end. Let me first finish this.
Yeah.
Okay.
It will be more helpful. Already 3 assignments are over, sir.
So if you have any doubts, you can ask me at any point. No issues in that. But I want to.
numerical problems in the assignment 2 and assignment 3. If you have, you can only 3 or 4 problems are there.
Have you seen
if
the
you discuss
solutions?
those problems, that will be more helpful, sir.
Have you seen the solutions of the problem shared by the team?
I have tried 1 or 2 problems. I have tried and I got, but only very few problems I could not solve.
So towards the end, I will come to that. Okay.
Okay.
Okay. Now the next point is, we have got the pressure volume diagram for the actual PV diagram, but in actually this pressure spring mechanism, it actually plotted the H, which is not equal to the swept volume length diagram, that is H, that is here diagram, which is calibrated and converted into PV diagram or indicated diagram. Indicated diagram. Okay. So what is there? If I say an example here, this was the PV plot. PV plot. Okay. This was the positive area, this was the negative area. So from the mean effective pressure concept, if we go for the same swept volume change, this is that height and this is the length. Okay, this h is this h of the system. Okay, this h is this h of the system. So let us say if my L is 2.5 centimeter. So from, and I know that the area, net area from positive and negative, net area is nothing but positive, negative. Okay, so it is given to be 7.5 centimeter square. So h into L, h is, we have to calculate 7.5. H will also come out to be some value. Okay, from here. All right. Oh, so h will come out to be, okay. So h is nothing but net area divided by the length. Okay, so h into SP is nothing but your mean effective pressure. So this L is nothing giving you an SP, that how much is the stiffness. Okay, the pressure per centimeter, the unit is pressure per centimeter giving you. H into SP, if spring stiffness is given to you, that is pressure per centimeter is given, into the height h is equal to indicated mean effective pressure. Now let us come to the question. Guru Prasad, just tell me one thing. Have you watched all the tutorials? Because I know that you joined in the first time in the previous tutorial, but for the first and second tutorial, have you watched those?
Sir,
Have you watched first and second tutorial?
last week video lecture and today's video lecture, I have only
you have-
watched, sir.
So you have not watched the first and second one, right?
Yes, sir. No, sir.
So that's why you are not able to cope up, I think so. Please go and watch the recordings first, because I have covered. Then you will be able to do the questions very easily and seamlessly. That's what
Okay.
I'm discussing. Yeah. And today also you joined late, so probably it might be a bit overwhelming for you currently. But I suggest that you just go back after the session and check the recording once again.
Okay, okay, sir.
Yeah, that will be much helpful, I think. And if still the doubt comes, because I have covered all the topics and with the questions, I have discussed questions in very detail. So that will be very, very helpful for you to understand. Still, if
Okay, sir.
any doubts come, please ask.
Only,
Okay.
only in assignment two numericals are there, and in assignment three numericals are there.
I get that, but you just have to watch just the concept, then only you can come back. If I just tell the solution directly, still you won't be able to get, because you have not watched the concepts first. Okay, I would just suggest you just to go back and watch those once again. Okay, next I'll come to the question. It's a very good question now. Following data are for the four-stroke, four-cylinder petrol engine. Cylinder dimensions are bore is given as 11 centimeter, stroke is given as 13 centimeter, engine speed is 2250 RPM. Brake power developed by engine is 50 kilowatt with frictional power 15 kilowatt Mass fuel rate is 10.5 kg per hour with calorific value of 50,000 kilojoule per kg. Air inhalation rate is rate m dot a is 300 kg per hour, and ambient conditions are 15 degrees Celsius and 1.03 bar. Find mechanical efficiency. Second, brake thermal efficiency. Third, relative efficiency. Third is not this. If relative efficiency is relative efficiency of engine is 60%, then find A, compression ratio, B, diagram factor. Do this question. It's a very good question. Each and every concept will be covered in this. I'll give you a few minutes to understand what will be the approach for solving this question. Then I'll discuss. Think that how you will approach for this question. Everything has been asked, what have been discussed. Most of the concepts with the numericals are covered from this till here.
Mechanical efficiency is 76.92%.
Okay. 76.92. Okay.
Second one is brake thermal efficiency.
What about others? Tennyson?
Brake thermal efficiency I am calculating.
Yeah. What about Santosh? Santosh, Tennyson, are you there? Swara? Okay, let's come to the solution first. So it is given that it's a 4-stroke 4-cylinder petrol engine. Dimensions D and L is given to you. Engine speed is given, N is given. Power developed by the engine, brake power is given, friction power is given. So you can get the indicated power from here. Mass fuel rate is given, calorific value is given, air inhalation rate is given, and ambient conditions T1 and P1 is given. Mechanical efficiency, brake thermal efficiency is asked. Let us get this one first. Solution. So first of all, let us get the swept volume from here. B swept is nothing but pi by 4 d square L into, it's a 4-stroke 4-cylinder engine. So K into N by 60.
Brake thermal efficiency answer is 34.29,
28.
sir.
Correct. Yes. So this will be your swept volume. You can just verify. So why 2 came? Because it's a 4-cylinder. So 2 revolutions are there. We have discussed this in the second tutorial. So from here, if you put all the values pi by 4, B is bore is given to be 11 centimeter, 0.11 square. Length is given to be 13 centimeter into 2250 by 60 into 2 into 4. Okay, so from here, it will come out to be 0.0926 meter cube per second, the swept volume rate. Okay, swept volume rate has come out. Now, it was given brake power was 50 kilowatt, friction power was how much? 15 kilowatt. So indicated power is nothing but brake power plus friction power. So 50 plus 15, that is 65 kilowatt. That is your indicated power. Okay. Mechanical efficiency, the first part is nothing but brake power to that of indicated power. So brake power is 50, indicated power is 65. It will be 76.92%. Also, we can calculate heat added per second. That is mass flow rate into calorific value. So mass flow rate is given to you as 10.5 kg per hour. So if I say in seconds, it will be 3600, and calorific value is given as 50,000 kg per kilojoule per kg. So it will come out to be 145.8 kilowatt heat added per second. So we know that what is brake thermal efficiency. We got the first answer. Then brake thermal efficiency, BTH, is nothing but brake power to that of heat added per second. We know that brake power is 50, heat added per second is 145.8. So from here, it will come out to be 34.28%. Then if I ask indicated thermal efficiency also, that will be indicated power to that of heat added per second. That will be indicated power is 65, heat added per second is 145.8. This will give me 44.57%. Okay, 44.57%. Now, it is said that relative efficiency is 60%, then find the compression ratio and the diagram factor. Also, let us find out the brake specific fuel consumption also. What will be, I'm taking out some extra things as well. So brake specific fuel consumption be mass flow rate to that of brake power. So mass flow rate is nothing but here 10.5 by 3600, and if you want in kilowatt kg per kilowatt hour, and brake power is nothing but 50. If you want it in hour only, then don't divide by 3600, just this much. It will come out to be 0.21 kg per kilowatt hour. Okay, this is a brake specific fuel consumption. Okay, then from here indicated pressure, you know that P indicated mean effective pressure into swept volume is indicated power. So P indicated mean effective pressure, swept volume, you know that you have already got pi by 4 d square L into 4 into, what was that? 4 into n by 16 to 2. N by 16 to 2. is your indicated power, that was 65 kilowatt. Put all the values, you will get P indicated mean effective pressure to be 7.10 bar. Okay, 7.10 bar. This also we got 76.92, 34.28. This also we got, and indicated mean effective pressure we have got. Similarly, brake mean effective pressure into swept volume is brake power. You have all the values. Brake power is 50 by V swept. P brake mean effective pressure will come out to be 5.39 bar. Okay, 5.39 bar. Okay. Now, what if I ask what will be the volumetric efficiency? So volumetric efficiency will be V A by V swept. V actual by V swept. So actual is lesser than the theoretical swept volume. So how you will get the actual value? Since initial conditions are given to you, P1 VA is equal to MR T1. T1 is how much? 1.03 bar in the question, I think so. 1.03 bar, yeah. And T1 is 15 degrees Celsius. Okay. So put the values. 1.03 into VA, and mass inhalation rate is given, that is 300 kg per hour, into is equal to 300 kg per hour. R is given, you all know that, 8.314 for the air, and T1 is 15 degrees Celsius, 273 plus 15 plus 15. So you will get, it was kg per hour. If I want to go with 3600 kg per second also you can get, or in terms of hour also you can get. So from here you will get VA in meter cube per second as 0.066.
Sir, you have written P1 value in bar. It
Yes,
should
yes.
be written in
10
kilonewton
to
per
the
meter square.
10 to the power of 5. You can multiply. Not an issue. Okay.
In
If you
place
want
of
to.
R, you have written 8.31 for sir.
Yes, 8 kilojoule per kilomole Kelvin.
In place of R, I think gas constant value we have to write.
What is that value?
Gas constant value 0.287 kilojoule per kg Kelvin.
Yes.
That value we have to write.
Okay. 0.287. Yes, you are right. R by mass of that gas. Yes, correct. 0.287. So from here, VA will come out to be 0.0668 meter cube per second in terms of SI units. Now put
P1
this.
units also, I think kilonewton per meter square we have to write.
So if we will go in that
Since
sense, it will
R
be 10
value
to the
we have
power of
written
2.
in kilonewton per
Yes.
meter square. P1
Yes.
should be also in kilonewton per meter.
Kilonewton. So it will be 10 to the power of 2 in that sense. Swept volume we know, we actually got. So volumetric efficiency from here it will come out to be 72.17%. This is your volumetric efficiency. Okay. Now what will be air fuel ratio? Air fuel ratio will be mass flow rate of air to that of mass flow rate of fuel. So we know what it's already given in the question, mass flow rate of air and fuel. So it will come out to be 28.57. Okay. Mass inhalation rate is given to you, MA. Okay. So from here we got all these values. Now relative efficiency is given to be how much? 0.6. If relative efficiency is given as 0.6, is given as 0.6. What is relative efficiency? We just saw it is efficiency of brake thermal to that of air standard. Brake thermal to that of air standard. Air standard. So air standard, how we will get the air standard value from here? Brake thermal efficiency we have already calculated. This is the brake thermal efficiency. Here, this one, 34.28. Okay. So it will be 0.3428 by air standard. So from here, air standard will come out to be 57.14%. And for a petrol engine, we know that air standard efficiency formula is, we have already derived 1 minus 1 by R to the power of gamma minus 1. So it is 0.5714 is equal to 1 minus 1 by R to the power of 1.4 minus 1. From here, the compression ratio will come out to be 8.34, which was required as in, okay, in the third part. And then last, what was asked? What is diagram factor? So diagram factor is indicated work done actual to that of indicated work done theoretical. So let us calculate that also. So air standard efficiency is nothing but indicated power from here theoretical to that of heat added per second. So we know that air standard efficiency is 0.5714. We want indicated power theoretical. Heat added per second we already know. We have already calculated above. We know that heat added per second. So from here indicated power theoretical will come out to be 83.31 kilowatt. So diagram factor is indicated power actual, that of indicated power theoretical. Actual we have already calculated, that is 65. It's given in the question, 50 break power plus 15, and this is 83.31. So from here the diagram factor will also come. Is it clear or any doubts in understanding this question? So what, let me tell in the whole scenario what we have done. We had provided some heat in the system, that is heat added per second. Okay, that was nothing but mass flow rate into the calorific value. Okay, that was 145.8 kilowatt. I'm telling about the energy, how the energy is being transformed. Energy transformation. Overall, I'm giving a sense, flavor of the sense that how what is happening. Then we reject the heat at constant volume. Okay, in the process, and we got some indicated power from the system. That was your theoretical power. We just calculated 83.31. Okay, 83.31 kilowatt. Then because of the presence of the water jackets, your indicated power actual will be lesser, that is 65 kilowatt. Okay, there was a loss. And because of the presence of the friction in the system, because every engine has some friction, so there will be a friction power. Because of that, we got a brake power output from that. That was 50 kilowatt. Okay, and this friction power was 15 kilowatt. Okay, so from this conversion to this conversion, let me show you. Heat added to this is giving you a air standard efficiency. From this to actual scenario, it is giving you indicated thermal efficiency. Okay, from heat added to brake power is giving you brake thermal efficiency. Then between indicated thermal, sorry, between brake thermal and air standard, between brake thermal and air standard and brake thermal is giving you a relative efficiency. Okay, and here also there is, because of the presence, there is a diagram factor coming here. Okay, from actual to theoretical. Is it clear or any doubts? This is the whole energy transformation which is happening in the cycle. Doubts clear?
QWJ means, sir?
Which one?
QWJ.
It is a
yellow color.
water heat taken out because of the water jacket. The actual PV diagram which we discussed. I think you
QWJ
joined.
means, sir?
Huh?
QWJ. You have
Q,
written in yellow color.
Heat
What is
interaction
that, sir?
because of the presence of the water jackets in the actual IC engines. So the actual PV diagram we have discussed in very detail. You have joined in a late half of the cycle. I've explained that thing here. This whole PV diagram with all the processes. I think you need to revisit this tutorial from the start in the recordings. Okay. So I've mentioned here QWJ is a water jacket, this yellow color. Okay. Any other doubts to anyone? So I hope everyone is able to see the lecture videos by the professor, the team, and my tutorial videos recordings and the PDFs are there. If you are not able to watch, and if you are new to the YouTube channel, for watching my videos, you can go to my YouTube channel, that is name NPTEL with Varnit, where recordings of this tutorials as well as in each video description for the particular course corresponding playlist, you will see the link of the Google Drive as well as the NPTEL team also share those who have registered in the course. So I think I can stop the recording in the midway. Let me just stop recording.